get started. Hope everybody's doing okay this morning. A little rainy, but otherwise nice. All right, so just a couple scheduled things. We got quiz 7 due on Wednesday, right, which you got last week. There's not another quiz this week because of the exam next week, but I am going to post it today because some of the stuff on that quiz will be on the exam, and I want you to have a chance to work through it and practice it. So it would be good if you finish the quiz before the exam, but if you can't, it'll actually be due the next week. Okay. So it'll be up there and you can work on it. So the exam will be a week from Wednesday. So that will cover, well, all the exams in this class are cumulative, so it'll be the beginning up through wherever we end on Wednesday. That will be somewhere in chapter 7, toward the end of chapter 7 probably. And we haven't skipped any, I mean, we've skipped around a little bit, but now we've actually done all of the chapters in order. So you can go from chapter 1 through chapter 7. That's what you'll see on the exam. All right, and other news, as you probably heard, there's possibility that Harper will have to close because of illnesses if the virus starts to spread around here. So we have been instructed what's going to happen in case of that. I don't know, has anybody heard that? Have you gotten information from Harper about it yet?
It didn't say much.
Yeah, it's a no. So what they've told us is if they have to cancel classes for a week or less, then we are expected to kind of make that up during exam week. So finals week will be we'll do some labs and stuff like that. So we'll still have class during that week. It'll just transition to an online format. So you'll have to pull up the videos. I don't know if you've seen, we don't usually put it up here, but there's a chat function in View 2 also. So if you're joining in from wherever, you can comment, you can ask questions, and so you can still do that when we're at home. So I'll plan on still streaming live at this time if we're not here. And what we'll do is we'll use the lab time to practice and maybe try to get a little ahead with the course material. So then when we come back, we can use some of the class time to make up the lab if we can. If the college has to close for more than a week, then they are expecting that all of the classes will meet their, meet their outcomes in an online format. So basically everything turns into an online class, and we're still expected to complete the semester that way. So, because there was some talk about would people get would you just get a refund and they just cancel the semester and nobody gets any credit? But we're already so far in the semester, I think we can finish up fine. So that's what will happen. As usual, whether or not you have this particular virus or any other virus, if you feel sick, please stay home, and you can always catch up online. You can always communicate with emails, and we'll work out the labs as we can.
Do we know that there are people here that do have it?
No, nobody at Harper has been confirmed to have it. So there's some people in Arlington Heights that are under basically they don't know if they've had contact with people who had it but don't necessarily have it. But there's not a widespread outbreak or anything around here yet. But probably only a matter of time, but we'll see when that happens. All right. So let's talk about some chemistry. All right, so getting into chapter 7. Chapter 7, we're going to look at another reaction, where chapter 6 we looked at a whole bunch of different reactions, or chapter 5, sorry, we looked at a whole bunch of different alkene reactions and different mechanisms and so forth. Chapter 7 is really just about a couple reactions, but we get a little bit more into deciding whether one reaction will happen or the other reaction will happen. based or the other based on the conditions. So to do that, we're going to look at some chemistry of haloalkanes. We've already looked at these a lot. This is mostly review, but we want to be able to practice recognizing them and naming them because that will come up. So let's just to review from a while ago, if you could please name these compounds. So to review, naming haloalkanes, how do we name the halogen part? It's fluoro, chloro, bromo, or iodo. Yep. So the rest of the naming is as usual, so see if you can come up with names for those three. Yes. Yeah. For that one you do because that would actually be the best number.
Yeah.
You go the other way.
Yeah. Yeah. Okay.
Timmy had a question about priority when it comes to halogens. So when there's halogens on the alkane, they don't get special priority the way that alkenes and alkynes did, or do. So those just are considered normal substituents like ethyl or methyl or whatever. All right, let's look at these names. So this first one should be one bromo, 2-methyl propane. Yep. Okay. Next one. Four bromo, 3,4. Whoops, hold on. Yeah. No, because the fourth carbon is the methyl. So the numbering is 1, 2, 3, and that's propane. And then the fourth carbon is the methyl group.
Oh, okay.
Yeah. So this one's going to be, 4 bromo, 3 methyl, 2, 1, 2, 3 pentene. And we aren't quite done that with that yet, because we have to specify that this is E. So remember, anytime you see any kind of stereochemistry now, whether it's EZ or RS, that should always be considered part of the name. What? The numbers? Yeah. 1, 2, 3, 4, 5. Both of these molecules, by the way, do have stereocenters and would be chiral if we picked one or the other. But in this case, they're not specified. So this would be a stereocenter here, and this would be a stereocenter here. All right, and then the last one. So this one's going to be 1R, 2S, 1 fluoro, 2 iodo, cyclopentane. Alphabetical order, so F comes before I. But as we've talked about this semester, I'm not concerned about the alphabetical order. But the important thing is they don't have like a priority over each other. It's just like, so you'd go fluoro, or bromo, chloro, fluoro, iodo, just because of the alphabet order. Methyl would come after that. Ethyl would kind of be in the middle because that's E. So just alphabetical order. All right. The other way you could name this, because it's in the special case of being a ring, is you could call it cis, because you only have 2 substituents in a ring. But if you had more than 2 substituents, or if you had only one, then you'd have to use the R and S designation. All right. Any questions about those? Okay. So the rest of this chapter, we're going to be talking about characteristic reactions of these haloalkanes. That is, what do they normally do? Now, there's lots and lots of ways that haloalkanes can react, but these are some very common basic ones that helps us to understand some organic reactivity. So the first one we're going to look at is something called nucleophilic substitution. And we've already sort of seen this, but we're going to get a little bit more into it today. Now we've talked before about what a nucleophile is. Let's review that. What is a nucleophile? Is what? Something electron rich. And what does it usually do reaction-wise? Yeah, donates electrons or attacks something or deprotonates something. Yeah, so a nucleophile we can sort of express in general as just Nu. And we're usually going to draw it with some lone pairs. Maybe it's neutral, maybe it's negatively charged. It could go either way, but it's going to be electron rich. It's going to be something that can donate electrons, that can attack something, attack another molecule to form a bond, whatever. So in nucleophilic substitution, you take a nucleophile and you take some carbon thing that has a halogen on there, and actually fluorine doesn't make much of a good leaving group, so we're going to stick right now to Cl, Br, and I. Later on we'll see some other things as well. And in the course of this reaction, because it's substitution, the nucleophile substitutes for the X. And so the nucleophile is attached to the carbon, and then the X is now on its own with its negative charge. So that's what we mean by substitution. So here's the nucleophile. And then the X part here is called the leaving group. And you can probably guess why. That's the thing that leaves. So the nucleophile comes in and attaches, and the leaving group leaves. And that's nucleophilic substitution. No. No, but we're going to focus on just the halogens for now. Actually, I have to change this so it doesn't get angry. Just a second. Maybe. Just a second, sorry. Okay. All right. So, does anybody remember what we've seen already that is a substitution reaction? I think it was from last Wednesday. We actually saw a substitution reaction in the chapter 5. Any ideas there? Well, I'll remind you. It was what? Somebody got it? Somebody say something? No? No?
The coordination with the acid, the HX one?
No, not quite. In that case, the nucleophile is still that's still considered addition. It's the alkyne substitution. So when we saw these acetylide ions, and then we could see that reacting with an alkyl halide like this. Let's draw that arrows. So the arrows we drew here, these come into the carbon and displace the chloride like that. And then the product that we drew of that is this. And then you've got Cl minus and Na plus. So making those carbon bonds, that's an example of a substitution reaction, a nucleophilic substitution. In this case, the acetylide ion is the nucleophile, and that makes the chloromethane, the alkyl halide here, the electrophile. The reason that that's an electrophile is because of the polarity of the CCl bond. So remember that we have a little bit of a positive charge on the chlorine and a little bit of a negative, on the carbon, and a little bit of a negative charge on the chlorine. And so because of that, the negatively charged nucleophile can be attracted to that carbon, and that starts the nucleophilic substitution process, which then kicks off that chloride ion. All right. So depending on the nucleophile that we use, we can now make all kinds of different functional groups based on this type of reaction. So actually, rather than write them all down, let's grab it from the book here. This is on page 196. There's a nice table of some different products of nucleophilic substitution. So as you see, depending on what you start with, if you start with an hydroxide nucleophile, you're going to make an alcohol because the OH is going to displace the halide, right? If you start with an O with some carbon stuff, you're going to get an ether because like OCH3 replaces that, and then you get that, and so on. Where it gets a little bit different, and that we'll see some examples of this, is when we have neutral nucleophiles. So down here we have ammonia, water, methanol. Neutral species can act as nucleophiles too. Do you think they're going to be stronger or weaker nucleophiles usually than the negatively charged ones? Probably weaker, right? Usually. So those are going to be reactions that happen in certain conditions but not in other conditions. So notice that when a neutral nucleophile reacts in a substitution reaction, the product is charged. It has a positive charge. And so then, like, the type of compound is still considered an alcohol, is a protonated alcohol. And so you'd have to have a proton transfer reaction after that to get rid of the proton. So a deprotonation reaction. All right, so let's practice some of these. So I'm going to write some reactions without products and then some products without reactants. And you're going to try to fill in the blanks. We'll do a couple together, and then you can work on a couple yourself. All right, so these are the kinds of reactions that we can look at now, where we start with some kind of alkyl halide, add a nucleophile, and then draw the product of the substitution reaction. So our first step here is we have to identify the nucleophile and the leaving group. So for that very first one, what is the leaving group? What? The bromine, right? The bromine that's on the cyclohexane. That's going to be the leaving group. So that's the thing that's going to be displaced. What is the nucleophile here? So what is going to substitute for the bromine? The NaOCH3 altogether is part of that. How is that going to look then as a product? What do we get if we substitute, that's called sodium methoxide, if we substitute that for the bromine? Can you see it? Yeah, so we have to think about what does this thing mean? What is sodium methoxide? So sodium methoxide is a sodium ion and a methoxide ion. So it's the conjugate base of methanol. If methanol is deprotonated, you have methoxide. That's why we often do this reaction in methanol as a solvent, because that way we have that proton transfer going back and forth if we're still making the same thing. So sodium methoxide in methanol, and that methoxide then can substitute for the bromine. And then our product is going to be this ether. And the other byproducts here would be sodium and bromide. All right, see if you can take a guess at the next two. The next one is basically the same idea, but with a different nucleophile. And the third one, we have a desired product, and we have to decide what kind of a what kind of a molecule to start with. Even if you're not totally sure, give it a try. Try to write something down there. See what you might use. What you might use right there. All right, got some ideas there? So for this first one, we're going to substitute for the bromine, recognizing here that the nucleophile is hydroxide. So our product should look like that. Okay. And then the second one, we have to do the opposite. We have our nucleophile, which is ammonia, so we're making an amine. So we just need to give some sort of alkyl chain with a leaving group. And that leaving group can be whatever we want it to be. So we need 1, 2, 3, 4, 5, 6 carbons, and then we add some leaving groups. So we could add bromine. At this point, we know 3 leaving groups: chlorine, bromine, and iodine. Any of those would work fine here. Yeah, Marina. What do you mean? Yeah, so this is the complete substitution reaction. In this case, the product is given, and this is the reagent, and so we supply a starting material. Right, the mechanism we don't have to write. We're going to go through that next because the mechanisms are actually could be a little bit different depending on what we're doing. Yep. Mm-hmm. Except for fluorine. Fluorine being really small and electron dense is not a very good leaving group. Yep. It's fine. I wouldn't mark it wrong if you use fluorine, but realistically, that's not going to be a great leaving group. All right, so let's look at our mechanisms. So one thing that happens with substitution reactions is even though the products are always what we show here, as long as you can identify the leaving group and the nucleophile, you can always draw the product because you just switch places. But they can proceed via two different mechanisms. So there can be two different pathways that this can take to get from starting material to product. And so we're going to look at those mechanisms now. Okay, the first mechanism that we're going to look at is called SN2. And we write that with a capital S and a capital N, but subscript, and then a 2. And that stands for bimolecular, meaning two molecules coming together at the same time, nucleophilic substitution. The reason it's called bimolecular and the reason it has the 2 in there, if you've looked at rate laws at all, I don't know if you've done that in previous classes, but the rate of the reaction depends on both the concentration of the substrate, that is the electrophile, and I've already drawn. But in bimolecular nucleophilic substitution, the important thing is that it is a one-step reaction, which means that it's going to have a reaction coordinate diagram like this. Where you have your starting materials on the right, your products on the left, and then a transition state, an activated complex in the middle that we have to have an activation energy to overcome. So the way that we sometimes draw this, well, here, I'll show you. The way that we draw this mechanism first is we say, okay, here's our nucleophile. In this case, we'll take hydroxide, and we're going to add it to some bromomethane, so just very small molecules so we can see it. And this is the mechanism that we've kind of been drawing up to this point anyway. So the hydroxide comes in, attacks the carbon. At the same time, the bromine leaves, and we end up with the hydroxide attached instead of the bromine, which is now a bromide ion. So that's it. That's the one-step reaction. The nucleophile comes in, the leaving group leaves. That's SN2 substitution. All right. So to get a little bit more detailed about what's going on there, let's be a little bit more careful with our geometry here. Even though this is not chiral, let's remember that this is in fact a tetrahedron, or tetrahedral structure. So when that hydroxide comes in, it really can only go in one direction, or in one spot. It has to approach the methane on the opposite side of the bromine. If you remember anything about molecular orbitals from Gen Chem, if you did that, that's where the antibonding orbital is going to be. So the electron density from the hydroxide goes in there, which then kind of causes the C-Br bond to break. So this has a couple consequences. One, we can draw our activated complex. So this is, remember, that transition state, that thing in the middle on the top of the hump that we never can actually isolate and see, but it just is kind of like the midpoint where it passes through. And this midpoint looks something like this. So let's say that the OH is partially connected to the carbon and the bromine is partially connected and partially leaving. So it's right at that halfway point. At that halfway point, the whole complex is going to look something like this. And we sometimes use this little sign of a line with two things on it to indicate the transition state, or that it's kind of like unstable, that it's in the middle. What kind of a geometry is that? You remember that from Gen Chem? We haven't really seen that this semester because carbon doesn't make 5 bonds. But if we sort of have these half bonds, does anybody remember what kind of a shape that is? I know, it's hard to remember back that far. It's called trigonal bipyramidal. Does that sound familiar at all? No? Okay. Well, anyway, it doesn't matter. But the important part of this is the 3 hydrogens here are planar now. They're almost like an sp2, like planar type geometry. And then you've got the OH on the one side and the bromine on the other side. And the consequence of that for when we actually draw the product is that the stereochemistry here will have flipped. Now this is not a chiral structure, so it won't actually, hold on, let me make this right here. Sorry. Oops. So let's see where we're going here. All right. So as the OH comes in the one side, that whole tetrahedral shape kind of flips like an umbrella. If you imagine the carbons and the 3 hydrogens being an umbrella, it's a windy day, the umbrella flips up like that, right? Same thing's happening with the hydrogens. The hydrogens were going this way, the nucleophile comes in from the bottom, and it flips it up to get out of the way. So if this were a chiral substrate, if this were a chiral electrophile, it would actually switch its configuration from R to S or S to R as a result of that nucleophile sort of pushing everything in the opposite direction. All right, so everything happens simultaneously there. And interestingly, I don't think the book talks about the stereochemistry of that. So we won't worry about that too much. But that's the one-step SN2 reaction. Okay. So now let's compare and contrast that with the other substitution mechanism, which is called SN1. So in a unimolecular reaction, it doesn't depend on 2 molecules coming together. One molecule kind of controls the rate by itself. So this reaction is actually 2 steps, which means that its energy diagram would look like this. And we'll talk about which things go there. But this time, instead of having everything happen in one step, we're going to have some like rate determining step with the higher hump. Actually, I'm going to redraw this so it's more obvious. The first step should be the rate determining step with the highest hump. The second step should be lower, like that. And then and so this is happening in two steps, and we'll talk about what those steps are now. So an SN1 reaction generally happens with things like tertiary alkyl halides. So a structure may be like this. Sorry. 2-bromo 2-methyl propane, or we might also call this tert-butyl bromide. Because in an SN1 reaction, the leaving group leaves first, and then the nucleophile comes in to displace it. So the first step of an SN1 reaction is just the leaving group detaching on its own, forming a carbocation. Now that carbocation, like others we've seen, is planar, sp2 hybridized. And that is the slowest rate determining step. After this, the nucleophile can come in and attack, and it can come from either side this time. So because the carbocation is planar, it's not like in the SN2 where the nucleophile can only come from one side. And this time it can come from any side. Generally, SN2 reactions involve neutral nucleophiles instead of charged nucleophiles. So let's say we have like methanol as our nucleophile. So instead of methoxide, which we saw in earlier substitution, we might use methanol as the nucleophile here. And again, that will attack from either side. Let's just draw one. Let's say it attacks like this. And then remember, when we're drawing mechanisms, we're always really careful about what's happening with the hydrogens. So all I've drawn with that arrow is the methanol attaching to the plus sign. I haven't lost any hydrogens yet. So that hydrogen is still there, which means that oxygen is now positively charged. So it's important when you're drawing your mechanism, both the alkene mechanism we saw in chapter 5 and these mechanisms here, keep track of what's going on with the hydrogens and make sure you're always drawing formal charges when they're there. So then the final step here to make the substitution product, the ether product, is for this to be deprotonated. And that is another fast step because this is just going to be in some methanol solution. So let's just say there's some more methanol around, and we can deprotonate to the final product. All right, so going back, if we look all the way across here, we can see that this type of substitution ultimately achieves the same thing as the SN2. So we still have our bromine here, and we're substituting the OCH3 for the bromine. Right. But in an SN1 reaction, it's happening in two steps. The leaving group leaves first, and then the nucleophile attacks. We actually drew a third step to deal with the deprotonation, but the actual substitution is only those two steps. So if we go back, yeah, Nicole. Mm-hmm. It is still there. Yes, if we're being careful, then yes, we should have. So we have like a protonated methanol here, and then we have bromine also hanging around.
What did you say? Leaving group leaves first, then?
Then the nucleophile attacks. So SN2, leaving group comes in, nucleophile leaves, all at the same time. SN1, leaving group leaves first, carbocation is there, and then the nucleophile comes in to attack the carbocation. So looking at our graph then, or looking at our plot of the energies, over here on the left, we see this is going to be our starting material, right? Everything unreacted. then our intermediate in the middle is the carbocation. And then the products are the products. Whatever is there. So you've got reactants, carbocation intermediate, products. Jerry. Yeah. All right, questions about that mechanism? Okay. So often this is not something that you get to decide what you want. So we don't often look at a substrate and say, let's say I would rather do an SN1 reaction on this one, and I would rather do an SN2 reaction on this one. It's more like we look at a reaction that's happening, and we decide what's going to be the most likely mechanism that it proceeds by. So to do that, we need to judge 4 effects to decide if a reaction will go by SN1 or SN2. And then later in the chapter, we're going to throw 2 more reactions in there that also compete with these. So there are four things that affect this. And they are the structure of the nucleophile, the substrate or the haloalkane, the electrophile, the leaving group, and the solvent. So what actual conditions that this reaction is being done in. So these 4 things will all affect whether or not the reaction is more likely to go by SN1 or SN2. Some of these are pretty intuitive, so we're going to go through them. But if we think about the reactions, so SN1, remember the leaving group leaves first. SN2, they all happen together. If you have a strong nucleophile, a much stronger nucleophile, do you think that favors SN1 or SN2? 2. But you're right. Why?
It's stronger, it's less stable, so it's going to happen faster.
Right. Exactly. Yeah. So SN2, it's all happening at the same time. If SN1 is going to happen, that means that the leaving group leaving and forming a carbocation is faster. So if it's a very strong nucleophile, that's not going to happen. It's all just going to happen at the same time. So a stronger nucleophile favors SN2 for that reason. So let's look at nucleophile strength, because it's not exactly correlated necessarily to base strength. Now the book simplifies it a little bit, which is helpful. Once we get into the second half of the chapter, we'll have to unfortunately complicate it back a little bit more. But let's take a look at some effectiveness of nucleophiles. Whoa, maybe not quite that big. All right. So here are some basic nucleophile, some nucleophile effectiveness measures. You can see that extremely good nucleophiles are negatively charged things that are also fairly big. So bromide, iodide, sulfides are extremely good nucleophiles, and oxides are decent nucleophiles as well. Medium nucleophiles would be smaller halogens like chloride and fluoride. More stabilized negative charges like carboxylates, which are resonance stabilized. And then neutral sulfur and nitrogen species are pretty like average, decent nucleophiles. And then the poor nucleophiles, things that are very weak, very slow nucleophiles, are neutral kind of solvent type molecules like water, ethanol, other alcohols, things like that are going to be, as well as acids, are going to be generally pretty poor nucleophiles. So generally, you're going to see SN2 reactions with the good and moderate nucleophiles, and you're going to see SN1 reactions with the poor nucleophiles. Again, as a general thing, that's only one thing to think of. We got to think of all four factors. But for this particular factor, we're generally going to favor SN2 with the good nucleophiles, SN1 with the poor nucleophiles. And the ones in the middle could kind of go either way, but they're generally going to favor SN2. Okay? Good with that so far? All right, so second is the substrate, the haloalkane. I've used a few different words for this. I want them to be kind of interchangeable. So we'll say substrate, which also in this case means haloalkane or electrophile. The thing that's being substituted on, the carbon thing. So there's a couple pretty clear rules and then one that's a little bit less clear. So the first thing that's going to affect this is carbocation stability. The more stable the carbocation, the faster it can form, although we know kinetics, like the stability and the speed, don't necessarily always go together, but in this case they do. So whatever can form a carbocation faster is going to favor SN1 because that requires that formation of a carbocation. So generally, where am I at here?
Whatever's going to form it or whatever's going to, because I thought don't going to have a carbocation because they're not very stable compared to the regular.
No, I wouldn't go that far. I mean, yes, they're not as stable as a neutral carbon, but because the ultimate product of a reaction might get you enough energy anyway, that if you can form something like a tertiary carbocation, they are stable enough to form pretty readily, actually.
It's whatever you can form, not whatever's already there.
Yeah, right. So I think we're saying the same thing. Let's take a look and see. So if you have something like this, which was our example from before, this can form a tertiary carbocation. Like that. We call that a tertiary carbocation. That's fairly stable. So if you have a situation like this, if you have a tertiary alkyl halide, so this one we could also call a tertiary alkyl halide, that would favor an SN2 reaction, or sorry, an SN1 reaction. Because that carbocation can form readily enough to just happen in solution. So as long as there's not too strong of a nucleophile around, as soon as you dissolve something like that substrate there in a solvent, it's likely going to start forming some carbocation in solution. So that's going to happen fairly readily.
Wait, so if it happens readily, wouldn't it be SN2 because it happens like kind of all at once?
No, SN2 is when the nucleophile attacks and the leaving group leaves all at once. I'm saying the carbocation just forms on its own fairly readily. So a tertiary carbocation favors SN1. But if we had something like this, if we imagine forming a carbocation there, which is now a primary carbocation, that's extremely not stable. In fact, that probably would not even form, even under the best situations. So probably this would not happen so much. And this would probably favor SN2 instead. So if you can make a tertiary carbocation that's nicely stabilized, you can have SN1 mechanism. If you can't, if you have a primary one, then you favor the SN2 mechanism. And you noticed I didn't talk about the one in the middle, the secondary carbocation, because that can kind of go either way. So if we have a secondary carbocation, we really need to look at the rest of what's going on, because we can't necessarily decide just from that. The second part of the substrate that influences which mechanism is steric hindrance, which we last looked at with our cyclohexanes. If we have a very crowded substrate, then the nucleophile can't really get in there to do the substitution. So that's going to favor SN1 as well. So we might say hindered or crowded. Hindered or crowded substrates favor SN1 because the nucleophile doesn't have any room to get in there to do the substitution. All right, so for example, so here's an example from the book. Let's say we have this molecule. Okay, big molecule. And we want to do a substitution to make an ether. We want to put a methoxy group on here. So we react this with methanol. Now, in order for an SN2 mechanism to happen here, that methanol would have to get up in here, because it has to come in opposite the chloride, which means it's got to get right in where all these rings are and all those hydrogens are sticking out, and there's just not going to be room in there. Besides which, that carbocation can be really stabilized by resonance with all these double bonds around. So likely what's going to happen here is, yes, we're going to make the product that we want. So the product would be the substitution of the chloride for the methanol. But because it's so crowded, this is going to be likely SN1 rather than SN2. So our chloride's going to leave, making a planar intermediate, carbocation intermediate. And now the methanol can attack, and because this is now a planar intermediate, there's plenty of room because it's nice and flat, and the methanol can come from either side. So the methanol can attach over here, or it can come from the other side. Either way. So that means that our product is going to be, after a proton transfer, so after we get rid of a hydrogen, we have our product as either this one, or this one. Right, either mirror image. So this one is S and this one is R. So that really hindered substrate means that the SN1 reaction is favored, and that leads to a mixture of enantiomers. So generally this is something that we want to avoid, like from a synthetic strategy. If you have something that's chiral, we've talked about how difficult it is to resolve enantiomers, to like separate a racemic mixture, or to separate enantiomers. So if you have a single pure enantiomer, you usually want to stop it from racemizing, from forming a racemic mixture. So this would be not a great reaction probably. We would probably want to pick a better nucleophile. So how could we, let's say we wanted to make that product, but we wanted to avoid the SN1 reaction. What would be a better nucleophile to use to allow us to avoid having this SN1 reaction and instead favor the SN2 reaction? We want the same product, but we want it to go SN2 instead. What could we do? What? What type of nucleophile do we need? Something stronger. So what's a stronger version of that nucleophile, of a methanol nucleophile? Let's go back up to our chart. If we still want to add OCH3, but we don't want SN1 to happen, instead of using methanol, we might use methoxide, CH3O-, which is a nice strong nucleophile that's going to get SN2 and hopefully give us the one that we want. Now, because this substrate is so crowded, it still might not work. So we might have SN1 regardless. We might always be stuck with SN1 with this kind of a substrate. But we could at least try and see. Methoxide, yeah. The conjugate base of methanol. So to kind of summarize that idea, if you're following along in the book, this is how they do that. Oops. Smaller so we can see it. If we look at our different possible substrates, so we can have primary, secondary, tertiary substrate, or even a methyl substrate, which is just, there's only one of those. So these things will never go by SN1 because they just cannot form a stable carbocation. And then a tertiary carbocation pretty much never goes by SN2 because it's just too crowded, too hindered. And then in the middle, you can kind of play with it and try to get it to go one way or the other based on some of these other factors that affect the reaction. All right, questions about that so far? Uh-oh. Angry. here at the computer again. Okay, and then there's two more. I don't know if we'll get to both of them, but let's look at the third one, which is the leaving group. So thinking about strengths of leaving groups, we can usually judge these pretty well because leaving groups are often negatively charged. And so whatever kind of molecule can best stabilize a negative charge, kind of like what we looked at in our conjugate acids and bases unit, can make a better leaving group. So anything that's a weaker base is going to have a greater ability to act as a leaving group. The weaker the base, the better the leaving group, because that means it's going to have be able to stabilize that negative charge well. So all the things we looked at about making stable conjugate bases in chapter 2 or 3, chapter 2, come back now, and that's how we can judge our leaving group ability. So things like OH minus hydroxide pretty much never act as a leaving group, because to have a stable neutral alcohol and then to have that break off into OH minus, which is a very strong base, is not really going to happen. But something like iodide, where you have this big atom that can distribute that negative charge all over it, is going to be a very, very good leaving group because of its ability to stabilize that negative charge. Same thing with the other effects we saw, things like inductive effects, resonance effects, all that stuff that deals with acids and bases also controls the leaving group. So the leaving group doesn't directly influence SN1 versus SN2 necessarily, because the leaving group strength contributes to both of them. So a good leaving group will accelerate both of those reactions. All right, so then we do have time to look at the very last effect, and then next week, on Wednesday, we'll look more at kind of applying this and putting it all together. But the last one is the solvent. So first of all, we pretty much always need polar solvents for these reactions because we're dealing with polar substrates. So completely nonpolar solvents usually don't work. If you look back at our examples, you can see everything we've been using is either extremely polar, like water or ammonia or methanol, or even charged, and actually ions, like sodium methoxide. This is ionic compound. That's not going to dissolve in like hexane or something, because it's an ion, and you need polarity. But what type of polar solvent you use can influence one mechanism versus the other. So we're going to split polar solvents into two groups. What we call protic and what we call aprotic. So polar protic solvents contain OH or something similar that can give off an H, whereas polar aprotic solvents do not have OH groups. So some common examples are protic solvents are things like water, ethanol, methanol, acetic acid, stuff like that. Those are all protic solvents because they have OH. They can give up H in solution. Aprotic solvents can still be polar but don't have any OH. So these are ones like a common one is this one called DMSO, dimethyl sulfoxide. Acetone is another one. dichloromethane. Right, these are ones that have polarity but don't have OH. And we're out of time, so we'll stop there and we'll pick this up on Wednesday and talk about the effects of that. If you want to work a little bit ahead, please read up on that and how we compare SN1 and SN2, because then on Wednesday we're going to throw some new reactions in there that also compare.
Can you give us some hint of what's left over? What are, where are differential starts, what is the percentage?
Where does it start? Well, so
Yeah, like,
yeah.
do you just throw in basic questions, just to make sure we're keeping up with what we should know from previous, or are you gonna get fancy and is there gonna be a lot of them?
No, it's more like everything we're doing now still depends on the stuff that we did before. So like, yeah. So like, if I want you to judge leaving group strength, you got to know acid and base strength, so it goes together. If I want you to name haloalkanes, well, you've also got to be able to name alkenes and alkanes and do the stereochemistry. So it's not like I'm just going to pull some obscure thing out of chapter 1 just to ask to keep you on your toes. It's more like everything we've done in those chapters is still influencing what we're doing in these chapters, and so it's all together. It all goes together.
Got it.
I have a question.